pleasure to, yeah, very good. Thank you for recording, right? It's my great pleasure to welcome you all to the first talk in this semester on our combinatorial seminar, and it would be given by Antonio Girao from Cambridge. Right, I will not talk too much about Antonio, so you can read his bio on the announcement of the talk. He has many great results and is a great speaker. And today he will talk about partitioning of a tournament into highly connected sub-tournaments. Please, Antonio.
Right. Okay, thank you very much, Benny, for inviting me. It's an honor. Okay, and good morning or good afternoon to everyone. Right, so I'm going to talk about a topic about when do a graph which satisfies the property robustly can be partitioned into several pieces, each of them satisfies the property. Okay, I should say first that this is joint work with Shoham Letzter. Right. Okay, so the meta question, maybe let me first state it, is, as I said, so given a graph property, P, when does a graph which satisfy P robustly, and let's see what that means, can be partitioned, or the vertex set can be partitioned into finite pieces, finitely many pieces, each of which has P. Right, okay, so for example, properties could be many edges, minimum degree, small maximum degree, highly connected, or high chromatic number. There's several properties of graphs. We can study each of them. Okay, so maybe let me start a little bit before, and instead of delving into this problem, let me say some very similar flavored problems which have been very well studied. Okay, so the first one I should mention is a lemma or observation by Erdős, which states that for any graph G with M edges, there is a bipartition of G such that the graph induced on AB has at least M over 2 edges. Right, okay. So this is essentially tight, we will see. And then, okay, so this is the number of edges. How about minimum degree? Okay, so another result, which I don't know exactly who proved, but just the greedy algorithm states that if G has minimum degree at least D, then there exists a bipartition such that the minimum degree of G induced on this bipartite graph is at least D over 2, rounded up. Right. And this is tight, for example, the clique. Okay, so, but for example, the other one, so the first one is not tight, and actually there's a result of Edwards, which states that actually there is bipartition with M over 2 plus some constant square root M edges. Okay, and this constant is known. But to prove for some constant is not hard at all. Right. Okay, and then maybe just say that Lee, Low, and Sudakov showed uh, 2013, so that actually there exists a bipartition where okay, the number of a bipartition where the size of A minus the size of B is at most 1, so they are essentially the same size, and the number of edges in this bipartition is at least m over 2 plus n over 6, provided, of course, okay, there's some bound on the max degree, let's say it's n over 3, and no isolated vertices. Right. So instead of, so there's many results where we know that a bipartition satisfies certain properties, but we want to know, is it true that there is a bisection? So actually a bipartition where both parts have essentially the same size, satisfying still the same. Okay, obviously we need I mean, this is important because otherwise a star, you can't have many, you can't have much more than m over 2 edges. Okay. Right, so, okay, what about, maybe let's just see K connectivity. So we could ask, is it true that a graph which is highly connected has a bipartition where the bipartite graph induced is connected? Okay, and this is a long-standing conjecture. Of Thomassen. Okay, and the conjecture states that for every K, there exists f of K such that every graph G, which is f of K connected, has a bipartition where the graph induced on this bipartition is K connected. Okay, so this is still open, and yeah, and I think the best bounds are like maybe like some function of K times log n. So depending on this order of the graph. Right, so now let's, okay, so that's what I want to say about what has been very well studied. So let's now delve into the type of problems we are interested in this talk. And okay, the first maybe result in this area is a result by Lovash from 66, which says the following. So suppose that we want to partition the graph where the maximum degree is small in each of the parts. Okay, of course, if the maximum degree of our entire graph is huge, then each part, there will be some part with still high maximum degree, so we need some bound on the maximum degree of the graph. So what he showed is that for any graph G, if delta of G is at most d1 plus d2 plus dk plus k minus 1, then, and d1 up to dk of integers, non-negative, then there exists a partition of the vertex set, say v1 unit vk, such that the maximum degree of the graph inducing vi is at most di. Okay, right, so, and this is tight by considering, for example, cliques. Yeah, so tight for cliques. So you can take, for example, di equals 1 for all I. And then if you have a clique on k minus 1, k vertices, sorry, maybe, let's actually say that di's are 0, and then you have a clique on k vertices, or k minus 1 vertices. Okay, so the minimum degree, so the maximum degree is at most k minus 1, is k minus 2, but if you partition into k parts, then there will be one part which has 2 vertices. Actually, yeah, there must be some problem here because, okay, I mean, up to
I think what you said in the beginning, k is good, right? So if you take k plus 1, it will not work, but k shows that it's tight, right?
Yeah.
You will have singletons.
Yeah. Okay. Sorry, this plus or minus, I always get really confused. Okay, so okay, so we know the maximum degree. So how about in digraphs. Okay, so we want, instead of maximum degree, maximum out degree, say. Okay, and here the problem is I mean, to show this, actually, maybe I should mention, is you can just optimize some weighted linear equation. I mean, it's not, it's essentially, I mean, it's essentially what one would do. Okay, but for digraphs, the question is a bit harder, and Alon using a very nice result of Keith Ball. There's some result on partitioning a matrix with satisfying certain properties. Maybe I shouldn't say too much, and then show the following. Okay, so theorem is a very similar statement, but now the di's must be a bit larger. So let D be a digraph. Okay, and the maximum out degree of D is at most maximum. So let's say 2 times the maximum degree of D is at most D1 plus blah 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 to dk plus k minus 1. Okay, so if you allow a little bit more, like these di's, then there exists a partition of the vertex set of D into k parts such that the maximum degree of D in Vi is at most Di. Okay. Again, this is tight for a regular tournament. So if you take regular tournament on 2k plus 1. Okay, it's either 2k minus 1 or 2k plus 1. Okay, and you take di's to be all 0, then I mean, yeah. So you will have one part will have at least 2 vertices, and so the maximum out degree it will be at least 1, and this is a contradiction. Okay, so this is tight. At least when di's are 0, it's not clear when di's are something different. Is not completely clear if this is tight. Okay, so now we've seen the maximum degree. Now let's go to the minimum degree, and this is a much interesting problem. So, okay, so the problem is the following. So for every k, is there some f of k such that every graph G with minimum degree at least f of k contains a partition such that the minimum degree in each of the parts is at least k. Okay, and this is not so obvious because you are not counting the number of edges. You want every single vertex to have many. So it's not, so I mean, this is a non-trivial exercise. Okay, let me state, so Hajnal independently Thomassen in 83 showed f of k exists, and okay, f of k is actually big O of k. Okay, let me give actually I'll give 2 proofs maybe. So they are short but nice. One of them based on the argument of Carsten Thomassen. Okay, maybe let me start here. So proof sketch. Okay, so you need. So I believe that there's 2 main observations, and the rest is more or less follows. So the first observation is that it is enough to find two disjoint sets V1, V2. So this is not necessarily a partition, it's just two disjoint V sets where the minimum degree is at least K for I1 and 2. Okay, and why is that? Okay, because suppose that here is V1 has minimum degree K, here is V2 minimum degree K. Okay, so then extend as much as possible V1 and V2, preserving obviously the minimum degree condition. Okay, so if there's a vertex here which sends at least K, then we add to V1 and try to do as much as possible. Okay, so then we have here some extensions. Okay, suppose there's a vertex outside. Well, this vertex either has, okay, if f of k is at least 2k, then this vertex either has k vertices here or k vertices there, in which case you can extend. Right, okay, so you can easily extend. So first reduction is it's enough to find two vertex disjoint. Okay, the second reduction is that it's enough to find V1 and V2, again, disjoint, not necessarily a partition, such that the average degree is at least 2k. Because if you have average degree, then you can pass to a subgraph with mean degree and then use one. Right. Okay. So now how do we find that? So let me give you first some random, maybe this nowadays would be the first thing one will try is random partition. Okay, so we start with our graph G, we just randomly partition. So say V1, V2, so put X in VI with probability independent. Right, okay, so what we know about, let's define X1 is the number of edges induced on V1, sorry, and X2 is the number of edges in V2. Okay, so we know that what is the expectation. We know this is at least the number of edges of G over 4. So each edge appears with probability 1/4. Okay. Okay, so this is not good enough because we want both to have many edges. But okay, but then as long as, so what you need to show is that the probability that Xi, say, deviates from the expectation more than E of G over 10. If this is less than a half, the same thing for both I1 and 2, then with positive probability, there's a partition where each of the Xi satisfies, has many edges. Okay, so it's enough to show this. Okay, and this looks like using the second moment. So we want to show that the expectation, like the variable is close to the expectation. So what one can do is just calculate the variance of Xi. Okay, and now I'm not going to calculate, but the idea is that every edge is independent of every other edge which doesn't touch, and it's only dependent of at most n other edges, or 2n. So every edge that touches is either 1 or 2. Okay, but that is, so the covariances will be 0 if they are disjoint, and then at most something smaller than 1 if they intersect. Well, but then you calculate that the variance is at most the number of edges times n. Okay, and that, because the number of edges at least k times n, I'm not writing because I don't think, I mean, you just, one does it and sees it, but you can show that this is this is little o of, I mean, they don't need little o, but it's definitely at most E of G times n or times 10n. Okay. Okay, and then we are done because the number of edges squared is much bigger than the number of edges times n over 10. Okay. So this is one way. A random partition now is what I guess this is what people do nowadays. But let's see another constructive argument, which is quite nice. So, okay, so the first thing is we pass to a bipartite. So again, use the lemma of Erdős, bipartite where let's say the minimum degree. So this is A, this is B, and say A is at least B, and the minimum degree of X is at least what, 100K for all X in A. We know that we have high minimum degree, so we can pass to a bipartite where the minimum degree is at least half. Okay, and now delete and make sure that so we delete edges incident with vertex in A so that this is an equality. So every single vertex in A has exactly 100K neighbors to B. Okay, and now split A into A1 union A2 of the same size. Okay, so let's call this A1, A2, they have the same size, and here is B. Okay. Okay, because they have the same size, the number of edges spanned here is the same, essentially the same as the number of edges spanned there. And because A is at least B, the average degree is still quite large. Okay. Okay, so now what we can do as the next step is just, okay, give an ordering of B, and now take the smallest interval such that either this part, or maybe I should put, or this part, okay, spans at least the number of edges of the graph over 10. So, so let's call this B star. So B star is the smallest interval. Interval, I mean, like starting interval. So anyway, I forgot the name for this. So you just have an ordering, and you keep taking vertices until either this part or this part spans many edges. Okay, so B is the smallest initial segment with number of edges from AI to B star is at least the number of edges in G over whatever 10. Okay, so we can assume without loss of generality that we have this is B star, that this is at least the number of edges of G over 10. Well, but okay, but by assumption, this is at most the number of edges. So the number of edges here is at most the number of edges over 10 plus, okay, maybe n. But n is going to be very small compared with this. And so we know that the number of edges coming from this guy to the rest, so B except B star, this is at least, well, 100K times the size of A2 minus the number of edges over 10 minus n. Okay, and this is at least 8K, the size of A2. Okay, which implies that the average degree of G induced on A2, B minus B prime is at least 2K. And similarly, okay, here you have 1/10 of the edges, so the average degree is large. Okay. Okay, so this is another option. Okay, so what about, sorry, please do interrupt if there is something that is not clear. Okay, so what about digraphs? Okay, so one would like is that if a digraph has large mean-out degree, we can split into two parts, both with large mean-out degree. Okay, and this is still very much open. This is a conjecture. Allen, maybe Nash-Williams had asked it before, but that's okay. So the conjecture of Allen is that for every k, there exists f of k such that maybe let me for something I want to say later, let me define this. For every k and s, there exists f of ks such that every digraph with mean-out degree, at least f of ks, has a partition with mean-out degree. So in vi, v1 at least k, and mean-out degree in v2 at least s. Okay, and so Allen showed if you want to partition into k parts, each of minimal degree 1 you can do. So it's true that if you have a graph with sufficiently mean-out degree, you can partition into k parts or k directed cycles. But for for the maximum, sorry. So this function is still not known, even f21 is not known to exist. Right. Okay. So for digraphs, the panorama is much bleaker. Okay. Now let's go to k-connectivity. Okay. So you could ask the same. Is it true that a graph with high enough, which is highly enough connected, there's a partition of the vertex set into two parts, each of them is k-connected? Okay. And again, in the same paper as this one, they showed both things. They showed the mean degree property and the highly connectivity property. Okay, and let me, because it's more close to what I want to say later, let me just maybe I should mention here before one thing. So even for the out degree, so it is known. This is known in the case of tournament. So it is known if kt for tournaments. So I guess you typically we don't know what happens for digraphs, so we look at tournaments, which are, I think a tournament is much closer to a graph because essentially directions can be viewed as edges or non-edges. And for tournaments, we know this exists, and actually is a very nice idea of Alon, Beng, Jensen, and Bessie. They show that f of kk equals 2k plus constant square root k. Okay, and this constant square root k is tight. Okay, up to the constant. And maybe why not? Let's just see. It's to prove some. Okay, let's just show. Let's show f of kk is at most 2k plus some constant k log, sorry, square root k log k. Okay, so if you allow an extra factor of log k, this is not too hard to show because the idea is just, okay, so proof, I mean, it's just a sketch. So you just start with your tournament. Okay, so the first thing is that you find a subtournament with mean for subtournament T prime with mean out degree at least the same mean out degree as T, and okay, which in this case I care. Let's say this is D. Okay, so and the size of T prime is at most constant T squared. Okay, so why is that true? That any tournament, I can find a small subtournament still with the same mean out degree. Well, essentially just keep deleting vertices. So yeah, so okay, the tournament has the property that the number of vertices of small out degree is small, because every tournament on 2D vertices has at least one vertex of degree at least D out degree. Okay, so using the observation that there are at most 2D vertices with out degree, sorry, smaller than D. Okay, so we use this observation, and what can we do is say, okay, let's look at the set of vertices with, look at T, and let's say this is the set of vertices with out degree strictly larger than D. So we know that, so these guys have out degree smaller than, so these are the guys with out degree smaller than D, strictly smaller than D. Okay, so of course, I'm not going to delete these guys, but I look at these guys and I say the following. Well, why can't I delete this guy and preserve still mean out degree? Well, these guys, if this was like this, I don't care because I lost maybe the out degree 1, but these have all out degree strictly larger than D. So all of these guys have out degree strictly larger than D. So for these guys, it's fine. Now, there could be, the problem is this. So if I delete this guy now has, sorry, okay, what I know that every guy has out degree at least this, okay. These guys have exactly D, okay? Okay, so then I delete this guy and I could have created a problem here. Okay, but these guys, there are at most 2D of these guys, we know. And if I look at the out neighborhood, this is at most 2D times D. Okay, so if I delete any vertex outside the union of the out neighborhood, I'm happy. Okay, so then that's why the constant D squared comes from. Okay, so now you pick this T prime, where the mean out degree of T prime is at least 2D. Sorry, is at least yeah, D. Okay, and now randomly split, and this works because it's just Cherenkov bound by Cherenkov. Because the number of vertices is polynomial in D, and the probability that you don't see K in its part is exponentially small. That's why you need this log factor. Okay. So we are happy. So now let's see K connectivity. Okay, and for K connectivity, the Hajnal and Thomassen showed, so Hajnal, maybe Thomassen independently. So in 83 showed any graph G with mean out degree, sorry, which is 100K connected, can be partitioned into 2K connected subgraphs. Okay, so it's linear in K. So what is the idea? I mean, I'm just very roughly just, okay, so we have, so we just applied, so if a graph is highly connected and the mean degree is high, then we find by the previous result two sets where the minimum degree here is high. is at least 50K. Now we use the result of mother to find here inside a K-connected subgraph. And same thing here. So mothers implies there exists V prime 1 inside V1 and V prime 2 inside V2, V prime I K connected. So just what it says that if you have average degree at least 4K, then you have a K-connected subgraph. Okay, and now, so it's exactly the same. Once we know that the entire graph is 2K connected and we have two vertices joined which are K connected, we can partition the entire thing. And so here is V1, V prime 1, this is V prime 2, this is K connected, both are K connected, and then, okay, just extend as much as possible, both preserving K connectivity, and now suppose there's something left. Okay, so let's say L is the leftover. Add the leftover to this extension. So look at that graph. If this is K connected, happy, we are done. Okay, if not, then there exists a set A, where the size of A is at most K minus 1 with at least two components. Okay, but one of the components must be inside L, because we know that this is K connected. So when I delete a set of size at most K minus 1, the leftover here is connected. Okay, so then there exists something here which is, so that this implies with two components, and one of them inside L. Okay, and now, so let's say C. So this is the component. Okay, and now, so again, so V1, V2, L, component A, component C. Okay, now add C to V2. Okay, if C union V2 is K connected, contradiction, because we extended as much as possible V1 and V2. Okay, so then there exists some A prime, where the size of A prime is at most K minus 1, and this disconnects. And again, there must be two components, and one of them must be inside C. Okay, so there exists C prime and inside C, but then A union A prime disconnects C prime from the rest. Right, okay, and then our graph was not, so only needs, so here only needs f of k to be at least 2k. For the other part, you need more. And there's a conjecture of Kriesel that f of kk equals 2 plus little of 1 of k. Right, okay. Now let's go to tournaments, because I want to say something. Okay. So why the tournaments? So first question is, okay, so first this was the conjecture of Thomassen. So obviously we are not going to do this for digraphs because we don't even know mean out degree. So of course being K connected is slightly stronger, so you start with something stronger, but it's not, I think it's much harder than even the mean out degree condition. Okay, so the conjecture of Thomassen is, can we do it in the setup of tournament? So for all K, for all K, is there f of K such that every tournament T has a partition where every f of K connected tournament T has a partition into parts where Ti is K connected. Okay, maybe it's just for the sake of we are on the same page. So a tournament or a digraph is K connected for every pair of vertices. there are at least k pairwise vertex disjoint or internally pairwise vertex disjoint paths, directed paths from X to Y. Right. Okay. So this was solved by Kuhn and Osthus and Townsend in 16. I should say this is from the 90s. And in 16, and they showed f of k. Okay, he actually showed the conjecture was a bit stronger because you don't want just two parts, you want t parts. But so let me just say what the Kuhn and Osthus showed. They showed that for every you choose k and you choose t, then every constant k to the fourth t to the 7, maybe the other way around, I can't remember, tournament, connected tournament, can be partitioned into t subtournaments where ti is k connected. Right. Okay, and they conjecture, same authors, Kuhn, Osthus, Townsend, they conjecture f of kt is big O of kt. And this would be typed by taking a tournament, a random tournament, say on 10 kt vertices. Okay. Maybe I should just say that Kim and Kang recently showed that f of kt is big O k to the 4 t. So it's actually is linear in t, but they couldn't get the linear in k as well. Okay, and that's what we show. So together with Shoham, we show that f of kt is big O kt. Right. Okay. So this is what we want to give a sketch of. Maybe let me say, why is it so much harder? Because okay, everything so far seemed not terribly hard. But why this is, I mean, I just want to convey that this problem is much harder than the graph case. Why? Okay, first thing, it is false. So one thing that really helps in the k-connected for graphs is this mother result, is that high average degree implies. This is very useful because it's much easier to track down edges than to track down k-connectivity paths between. Okay, but it is false that any tournament with arbitrarily, okay, so it is false, or there are arbitrarily tournaments with, there are tournaments with arbitrarily large mean out degree without a subtournament which is k-connected. Even two connected. Okay, so we cannot use mean out degree conditions. Okay, second thing, it is false. Okay, so the two main observations, which are very nice, is, okay, one, tracking number of edges is enough via mother. Second, once you have two vertices joined, you can just extend. This is false as well. So it is not true. It is enough to find T1 union T2. Okay, not necessarily partition. Well, not a partition, otherwise will be with Ti k-connected. So it could be that somehow the k-connected parts you found are very much needed you can't just extend because some of these guys have the complete out degree here and the complete in degree there, something like that. Okay, so you can't just find, okay, so then these are two main obstacles which one needs to do something. Okay, so let me give a proof sketch. Okay, maybe I don't think I will have time to give definitely all the details, but let's first prove for the case t equals 2, because all the ideas are essentially here. And so we'll show that fkk, fkk is just two parts, each k connected, is at most constant k log k. So let's prove this slightly weaker, but all the main ideas are essentially here. You have to be much more careful in the general case. Okay, so the first step is to find some nice gadgets. So what are the gadgets? So each gadget comprises of the following. Okay, so you have two transitive tournaments. Let's call sorry, this is not, it's called the source S plus and the sink here S minus. Okay, this has size constant log k. And there will be a directed path from the sink of one to the source of the other. Okay, and so we find constant k many such gadgets. Okay, but what are the gadgets? I mean, what properties do they have? Okay, so let's say, so the first property we are interested in is that for every gadget, let's call gadget G. So this is GI. So for every GI, there exists some bad set V associated, where the size of the V bad is at most the size of the tournament over k cubed. I mean, the numbers here are not so important, as long as it's a polynomial in k. And so what are these bad vertices? These are the guys which don't send an out edge or an in edge to either here or here. So, and for every x not in the V bar, x sends an out edge to maybe for sake of notation, let's call this S plus, S minus. So sends an out edge to S minus and in edge to S plus. Okay. The second property, and this is one key property, is that for almost every vertex in this gadget, so we know that these transitive tournaments are small size, constant log k, but this path we have no control. So this path could be n over k or something huge. So what we want to say is that for every vertex, or for almost every vertex in the gadget, I'm going to put, because I don't want too many quantifiers, so for almost all vertices in GI, the difference of the out neighborhood of S minus for almost every vertex, let's say X in GI, the difference of the out neighborhood, maybe let's put this. So the number of vertices in the out neighborhood of S minus, which are not out neighbors of U, is very small. Is at most say K. This again is not so important. And the same thing for the other guy. Okay. We'll see how we can get that. And okay, and then we have some other property that the mean degree of X, the mean out degree is at least the size of V bar times K. Okay, actually, okay, V bar could be 0, so this doesn't make sense, but it's at least the max of V bar K or K, constant K log K. Okay, why these properties can be satisfied? I mean, the first property is, okay, I'm not giving all the precise because we want to find these gadgets at the same time. So this is the issue. So how do we find this many? So we want to find constant K gadgets at the same time. So what we do is, okay, we find X1, X2, Xk, or constant K, which are the vertices of highest out degree. And now we take Y1 up to Y constant K of highest mean in degree. Okay, and now we go to Y1, we look at the out neighborhood, we delete the out neighborhood, go inside, pick another vertex of highest out degree, and so on. So this is eating at least a half, because the out degree of any tournament on K vertex is at least half of its size. It's eating at least half. So once I have here some constant log K vertices, then we know that the number of, and same thing for here. Okay, and you see that the way I've constructed is for every vertex, I delete the out neighborhood. So the second guy will be directed to X1 and so on. So this will be a transitive tournament. And all of these will be like this, and all of these will be like that. And by assumption, we have immediately the property A, because the guys that don't send an in edge there or an out edge here is at most the size of the tournament over 2 to the number of vertices. So 2 to the constant log K. Okay, and then you take the union of all these bad over all gadgets, and this is at most K times, I mean, it's another factor because we have constant K gadgets. Okay, so the total set of bad guys, now this is the V bad over everything, and these are the guys which do not send an out edge to every guy here, and at least an in edge to every guy there. Okay, and this is small. Right, okay, and now what we want to do is, okay, so we pick this S minus, as we pick this as S plus, and now we find this, sorry, I think I made a mistake. This is like this, sorry. This is, you take the entire in neighborhood and then you delete, so this is going to be outwards here. Okay, so you pick this and you pick that, and now you just, we know the graph is constant K connected, so we can find vertex joint paths that do this. So link and so on. Okay. Okay, and now we take these paths as small as possible. Right, okay, and now I claim that if you take these paths as small as possible, this is going to be true. Why is that? So let's just see one case. So we have this, we have the tournament here, this is the S plus, we have something here, this is S minus, and we have this path. Okay, now suppose, okay, that remember that I said for almost all vertices in the gadget. So maybe there are some vertices, but so let's not count these guys. But suppose there's a guy here, and this guy sends an out neighborhood to this guy, and this guy, okay, and I don't look at the first, say, 3 guys in the path. Okay, but suppose that this sends an out there, and this is not in the union of the other gadgets. For let's assume that for now. Well, then I could have decreased the order of the path. So we know that this guy must send the same out, must send an out neighborhood to exactly the same out neighborhood of S minus. Otherwise, I could have shortened the path. Okay, same thing. If I have this and I have this, and suppose that this guy sends, sorry, suppose this guy sends many edges here. And now let's forget maybe the first in this, so the path goes like that. Let's forget the first 3. And suppose this guy has a neighborhood, which is an out neighborhood of this, which is not an out neighborhood of that. Okay, but then we could go like this. We could have decreased the path. So you go like this, you go there, you go like that, and you could go, sorry, you go like this. Okay, so apart from maybe 3 guys, and this decreases the order of the path. So apart from the last 3 guys, we can say that all these guys have the same out neighborhood as that. Okay, so we have property 2, and the last property is just is the way I've constructed, follows immediately. Okay, so we are essentially done. I mean, with some, we need some step 2, which is some cleaning. So we delete some of the gadgets to make sure that every vertex now, remember that the vertex here, which could be, because the path could be huge, I know I can control exactly where the out neighborhood is, because we know it's essentially the same out neighborhood as this, and essentially the same in neighborhood as that. So we have only like constant k log k in total vertices we need to control. Okay, and we randomly delete gadgets, so this is the leftover, such that every vertex now sends many edges, sends at least constant, some other constant k log k outside the set of gadgets, out and in. This is easy, just a random partition, and then just being a bit more careful, because some guy could have all its out neighbors inside one gadget, and then that's the probability that that gadget will not disappear is not that big. So I mean, you have to do some cleaning, but it's not too hard. Okay, so every vertex sends many to the leftover, and we know that this is the bad guys, and every guy we know sends at least a large constant times the size of the bad. Okay, so then the only thing you need to show, the claim, and I stop here, is you randomly partition this thing into 2 parts. And what do I know? I know that every vertex, the number of vertices I need to control here is at most k log k. So with high probability, every vertex here, okay, let me maybe say, so first we split the gadgets into 2 parts irrelevantly. Okay, so we have constant k of them here, constant k of them here. Every vertex here sends an out edge to each one of these, and every vertex sends an in edge to each one of these, and same thing here. Okay, now we have to control the out neighbors of this constant k log k, but then randomly, with high probability, I will see some in its own part. So I put just, I randomly partition this, and I put L1 with these first guys, and L2 with these second guys. Okay, so these guys are happy. These guys will see at least k out by just this property. Every guy will see k out neighbors there and k in neighbors there. Every guy here will see k out neighbors there, k in neighbors there. So the only problem is what happens with v bar. Well, but for v bar, we know that out neighborhood and in neighborhood outside the v bar is very large because it's at least k times the size of v bar. So you must send many outside. So then another chain of bound says that every single guy here must send many edges outside. Okay, and these ones will, with high probability, will be in L1. If this is, I mean, you will have half in L1 and L2. And then we are done because, okay, we have a union of gadgets with some left over where every vertex sends, so every vertex sends at least k here, and to a part where every vertex sends at least k to each one of these. Sorry, there's k of them, and each sends one to each, and same thing for in degree. Okay, and every guy here sends at least k out and k in. So this is enough to make this k connect. Because all of these, we know all of these have a path connecting from the sink to the source. Okay, I mean, I'm sorry I have to rush a little bit in this last part, but maybe if you have now questions, I can explain a bit more. Okay, thank you.
So maybe thank you, but you can unmute yourself. You can thank Antonio for the great talk. Thank you, Antonio. And indeed, it's a good time to ask questions. If you have, I think you can unmute yourself and just directly ask questions. Yes. I guess how things were.
I don't think I explained that well, not to have questions.
The end, I think, was right indeed a bit fast, but it's clear not a simple. But the fact that the gadgets help you to preserve K connectivity, I think was
and in the case where you don't have this, so the log K really helps because I can say that the union of the bar is very small, and this is quite helpful. And when we don't have this log K, I mean, each gadget will have an associated bar. Then you must look at vertices which don't send many out edges to most of the, I mean, there's a lot of most of vertices send most, and there's a lot of tracking down these, but.
No, I see. I understand. I mean, log helps you, right, with all the random things as well, right? So this.
Yeah, exactly. Yeah.
You will need to substitute it with some big constant and then do some more average type analysis, which would be probably computationally challenging.
Yeah.
So what would be, just maybe curious, right? So we know it for tournaments, it's extremely hard for digraphs. So is anything in between where we might still?
So there are, there are few questions, which, one of them is, what about prescribing the sizes of each part? Or what about maybe the most interesting is an equipartition? Okay. Right. We think that our proof gives, so I was talking with Shoham, but it's like, I really don't want to go through that. But one thing that me and Shoham also have proven, I mean, eventually will come out, is the graph equipartition. So a graph with mean out degree at least big O K T can be equipartition such that each part has mean out degree K into T parts. But there are So one, okay, so there's another interesting type of question, which is, maybe I can, if I have like 2 minutes or 1 minute, I can just say is that, so Kuhn and Osthus show that there's another type of partition. So if you have high mean-out degree in a graph, then you can force a partition where this has still mean-out degree large, this as well. And one of the parts also sends many edges to the other part. You can't impose both directions, but you can impose one-sided. And why is this nice? Because this allows you to embed. Okay, why these partition problems are interesting is because if you know that some property implies the existence of something, then okay, with a bit more robust of that property, you can get many copies of that copy you wanted, of that structure you wanted. And here, and this structure is quite nice because here I can find, so for example, if you can, this will, a slightly stronger version of this would prove low-vas there's a conjecture of low-vas where if a graph is highly connected, every 2 vertices there is a path for which the removal of the path makes a k-connected graph. And if I could impose that x and y are in this part and this part is k, so they also prove the k-connected version. So k-connected, and every guy sends at least k edges. So if I could prove that I impose that x and y were here, then okay, this is k-connected. I mean, I just get this to be connected, this part. So I just pick a path, I delete, and then I absorb the vertices in this k part, and each guy sends at least k edges, so this thing will be k-connected. So this would prove low-vas conjecture, provided I could force my x and y to be in the same part, and in this specifically in the part that sends many edges to. And for example, there aren't that many bounds, that very good bounds for this type of problem. And but for digraphs, I don't think. I mean, some people have looked at semi-complete, but I don't know if that is very interesting.
Okay, great. So thank you again, Antonio. So I think we can stop recording.